The topic of this lecture is allylic bromination. Allylic bromination is a free radical halogenation of alkanes containing double bonds. For the most part, free radical halogenation reactions are not particularly useful to synthesize products because we get a mixture of products. For example, if we perform the free radical chlorination of pentane, we'll get a mixture of products. Take a moment to pause the video now and see if you can draw all of the possible monohalogenated products of pentane that we would get in this reaction and label them major and minor. There are three possible products that would result from the monohalogenation of pentane. We would get 1-chloropentane, 2-chloropentane, and 3-chloropentane. 1-chloropentane, which results from a primary radical, would be the minor product. 2-chloropentane and 3-chloropentane, which result from secondary radicals, would be the major products. Because we get a mixture of products, this is not a particularly useful synthetic reaction, and for the most part, free radical halogenation is not useful except in special cases, such as, for example, if we try to monohalogenate cyclohexane, we will get only a single product. Because of symmetry, there's only one type of hydrogen on this molecule, so we only get a single product. The other type of special case involves reactions where there is a single, very stable radical that can be formed. For example, if we try to brominate 2-methylpropane. Because bromination is so much more selective than chlorination, we will only get the very stable tertiary radical, which will give us a single product. Another example of a molecule that has a very stable radical are allylic compounds. An allylic position is a position right next to a carbon-carbon double bond. A radical on the carbon next to a double bond is very stable because it is resonance stabilized. Take a moment to draw these two resonance contributors in their Lewis structures so you can tell what's going on. Lewis structures for these resonance contributors look like this. Because of the stability of the allylic radical, combined with the fact that bromination is so selective, we can choose some reactions of allylic bromination that will give us a single product. For example, let's look at the radical bromination of cyclohexene. The radical bromination of cyclohexene gives us a single product in very good yield. The reason that we get a single product is because of the stability of the allylic radical combined with the selectivity of the bromination reaction combined with the symmetry in this molecule. There are two allylic positions, but bromination at either of those two positions gives us the same product. Now let's look at the mechanism. The first step of radical halogenation is abstraction of a hydrogen atom. This can occur at the allylic position or at the position next to the allylic position. Abstraction of a hydrogen from the allylic position gives us the allylic radical. This radical is resonance stabilized. Take a moment to draw the other resonance contributor for this allylic radical. The other resonance contributor looks like this. Because of the symmetry in the molecule, the next step of propagation, which is addition of bromine to the radical, will give us the same product no matter which resonance contributor reacts. In both cases, we get addition of bromine to the allylic carbon of the molecule. Now consider what occurs if we abstract a hydrogen from the position next to the allylic position. This results in a secondary radical that is not resonance stabilized. Because the secondary radical is so much less stable than the resonance stabilized radical, it does not form, and we don't get any of the product that would result from this radical. Because of the selectivity in allylic bromination, this is a very useful reaction in organic synthesis. However, side reactions can occur if our concentration of bromine is too high. Side reactions are bad because they produce additional products that we then have to remove using purification. We'll talk about some of these side reactions later in the semester. However, what I want to focus on now is how we avoid these side reactions in allylic bromination. We do this using a molecule called N-bromosuccinimide. N-bromosuccinimide allows us to maintain a constant low concentration of bromine, which allows these allylic bromination reactions to work without producing side reactions. N-bromosuccinimide, or NBS, produces bromine in the presence of HBr. You do not need to know the mechanism for this reaction. N-bromosuccinimide is used in allylic bromination reactions to replace bromine. For example, the reaction of propene to give bromopropene. In this case, we've replaced bromine, Br2, with NBS. Note that we still need to use light or heat to activate the radical reaction.